Every single night, you can step outside, tilt your head back, and spot planets with nothing but your own two eyes. Mars, Venus, Saturn, Jupiter, every single one of them, visible, naked, raw against the dark. Every one except one. One planet sits so far out, so isolated at the edge of our solar system that it remains permanently invisible to the human eye. And that planet is Neptune, the last giant, the most overlooked, and without question, the most bizarre world orbiting our sun. Because nothing about Neptune should work the way it does. And yet here it is, defying physics, rewriting our assumptions, and sitting quietly at the edge of everything we know. Let's go back to the beginning. Every planet in our solar system was found the same way. Someone looked up and spotted it. Except Neptune. Neptune was never seen first. It was calculated, predicted on paper before a single eye ever found it in a telescope. Here's how it happened. When astronomers mapped the orbit of Uranus, something was wrong. The numbers didn't line up. The planet kept drifting off its predicted path, as if something unseen was tugging at it from beyond. In 1846, a French mathematician named Urbain Le Verrier ran the calculations and told astronomers exactly where to point their telescope. Johann Galle did exactly that and found Neptune less than 1 degree from the predicted spot. Not approximately, not roughly, 1 degree. That moment remains one of the greatest intellectual achievements in the history of science. Mathematics revealed a planet before human eyes ever could. Shortly after, Triton, Neptune's largest moon, was discovered. But beyond that first look, the planet stayed mysterious for over a century. It was simply too far away for ground-based instruments to study meaningfully, too small in the sky, too distant to resolve properly. For 143 years, Neptune was essentially a dot with a name. Then, in 1989, Voyager 2 made its historic pass. Suddenly, images flooded in, rings were confirmed, new moons were found, a storm the size of Earth was captured swirling across the surface. That single flyby rewrote everything we thought we knew about the outermost giant and raised 100 new questions in the process. So where does Neptune sit in the grand order of things? Since Pluto was reclassified, Neptune holds the title of 8th and final planet. It orbits at roughly 30 AU from the Sun, 30 times the distance between Earth and our star. Translated into raw numbers, that's 4.5 billion kilometers of empty space separating us from it. To cross that gap with current spacecraft technology takes approximately 13 years of continuous travel. A full orbit around the Sun at that distance takes 165 Earth years, which means in all the centuries since Neptune was first discovered, it has completed exactly one solitary lap. We witnessed the entire thing. That single fact alone captures just how staggeringly large our solar system actually is. The average atmospheric temperature out there settles at around -201 degrees Celsius. That is, by any standard, brutally cold. Neptune's axial tilt sits at 28 degrees, remarkably close to Earth's 23 and Mars's 25, which means it experiences recognizable seasons: summer, autumn, winter, spring. The difference, each season lasts 40 Earth years. Right now, Neptune's southern hemisphere is moving through spring. As sunlight, already 900 times weaker than what Earth receives, hits the southern region, temperatures there climb roughly 10 degrees above the planetary average. That small thermal nudge is enough to release frozen methane locked in the troposphere above, causing that hemisphere to visibly brighten. A 10-degree shift, 900 times less sunlight than Earth, and it still makes a measurable difference. Neptune doesn't miss anything. Here is where Neptune stops making sense. If you line up every planet in our solar system and ask which one has the fastest winds, the logical answer is Jupiter. Biggest planet, most powerful gravity, closest gas giant to the Sun. But the answer is Neptune. Wind speeds along its equator hit 2,160 kilometers per hour, blowing westward, nearly supersonic. For context, the fastest wind ever recorded on Earth barely touched 400 kilometers per hour. Neptune almost hit 6 times that. And the truly disorienting part? Most of those winds blow in the opposite direction to the planet's own rotation. The atmosphere is moving against itself and doing it faster than any other world we've ever studied. When Voyager 2 arrived in 1989, it photographed a colossal storm system raging across the surface, named the Great Dark Spot. It was comparable in scale to the entire Earth. A second, smaller storm was also captured nearby, and as Voyager watched, that smaller storm visibly shifted in color from dark to light during the approach. When the Hubble Space Telescope was eventually aimed at Neptune a decade later, both storms had vanished completely. Gone. No trace. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's storms appear, rage, and dissolve on their own unpredictable schedule. Massive bright cloud formations at high altitude do the same, materializing and disappearing without consistent pattern. Neptune's atmosphere is not just active, it is chaotic. Now here's a question that demands an answer. Neptune and Uranus are nearly twins, same size category, same basic composition, same distance range from the Sun. So why does Uranus sit relatively calm while Neptune tears itself apart with hypersonic winds and planet-sized storms? Something beyond solar interaction has to explain the gap, and the answer almost certainly comes from deep underground. Neptune generates its own internal heat and radiates it outward into space. Uranus, by contrast, emits almost none. The leading theory is that a massive impact, an object roughly Earth-sized, struck Uranus billions of years ago and drained it of the primordial heat it had carried since formation. Neptune kept its heat. That retained warmth drives convection, fuels atmospheric instability, and ultimately produces weather that makes every storm on Earth look like a mild breeze. What is Neptune actually built from? Its atmosphere breaks down to roughly 80% hydrogen, 19% helium, with trace amounts of methane. It's that methane that filters out red wavelengths and reflects blue light back outward, giving Neptune its deep, rich blue color. Darker than Uranus, more saturated, more intense. Beneath the atmosphere lies a thick liquid mantle composed of water, ammonia, and methane ices. And at the boundary between that mantle and the rocky core below, pressures become so extreme, around 7 million times Earth's surface atmospheric pressure, that methane molecules fracture, carbon atoms break free, and under those crushing conditions, they may crystallize. What could exist down there is genuinely extraordinary, a liquid ocean of carbon with solid diamond formations floating through it like icebergs and diamonds precipitating downward through the mantle in a continuous slow rain. This remains theoretical. Laboratory technology has only recently begun reproducing such pressures in controlled settings, but the physics support it. Neptune may be raining diamonds right now. Neptune's magnetic field adds another layer of strangeness. It's offset from the planet's rotational axis by 47 degrees. When Voyager 2 found this same offset on Uranus, scientists assumed it was a side effect of Uranus's extreme axial tilt. Then they found the identical offset on Neptune, which has a perfectly normal tilt. That theory collapsed immediately. The current explanation is that Neptune's magnetic field isn't generated in the core as it is on Earth, but instead emerges from the electrically conductive liquid mantle surrounding it. Or alternatively, that same mantle deflects the core's magnetic field, skewing it dramatically off-axis before it reaches the surface. Every planet carries some degree of magnetic misalignment, but only Uranus and Neptune show offsets this extreme, and neither has yet fully explained why. Auroras exist on Neptune, though nothing like you'd see on Earth. They're faint. Particles arriving from the Sun carry less energy at that distance, and because of the magnetosphere's unusual orientation, they don't cluster at the poles. Instead, they form at mid-latitudes, wrapping around the planet's midsection in dim, diffuse arcs. These are classified as SAR arcs, the same category Earth produces, though ours remain invisible with scientific instruments. On Neptune, they could be quietly illuminating enormous stretches of sky at this very moment, completely unobserved. Pull back far enough from Neptune and the rings come into view. Like every other gas giant, Neptune carries a ring system, 5 confirmed rings in total, each named after a scientist connected to the planet's discovery or study. The innermost is the Galley ring, broad at nearly 2,000 kilometers wide, but almost impossibly faint. Next comes the Leverrier ring, narrow at 113 kilometers, but noticeably brighter. Adjacent to it is the Lassell ring, a wide, diffuse band stretching 4,000 kilometers, and at its outer edge, the Arago ring, slightly more defined, under 100 kilometers across. The outermost and most studied is the Adams ring, only 35 kilometers wide but among the brightest, and it holds something no other ring in the solar system fully replicates: stable arc formations. Within the Adams ring, material has clustered into concentrated bright arcs instead of spreading uniformly around the band. These arcs have held their shape since they were first detected in 1980. That should not happen. Ring material is constantly moving, colliding, and redistributing. Stable clumping over decades contradicts standard models of ring dynamics. No confirmed mechanism has yet explained why Neptune's outermost ring refuses to behave like every other ring system we know. It's one of the most straightforward-looking anomalies in planetary science, and one of the least resolved. Neptune hosts 14 known moons, each named after a deity from Greek aquatic mythology. By far the largest and most significant is Triton. Triton contains more mass than all of Neptune's other moons combined. It is larger than Pluto. It carries its own thin atmosphere. Voyager 2 photographed faint cloud formations during its 1989 flyby, clouds on a moon billions of kilometers from the Sun. But the most telling detail about Triton is its orbit. It circles Neptune in retrograde, moving in the opposite direction to the planet's rotation and at a significant inclination. No moon that formed alongside its planet does this. The orbital signature is unmistakable. Triton was captured. It once traveled independently through the outer solar system, was pulled in by Neptune's gravity, and has been locked in orbit ever since. The gravitational disruption caused by that capture likely destabilized other moons already orbiting Neptune, triggering collisions that shattered them into the debris now forming the ring system. The second largest moon, Proteus, presents its own puzzle. At 400 kilometers across, it exceeds the diameter of Mimas, one of Saturn's spherical moons. Objects that size are typically massive enough for gravity to pull them into a sphere. Proteus is not spherical. Its shape is irregular, distorted by the remnant craters left by historic impacts, severe enough to have almost broken it apart entirely. It is, by any measurement, a moon that barely survived becoming something else. The inner moons orbit within and around the ring structure, several functioning as shepherd moons, gravitationally corralling ring material and maintaining the edges of specific bands. The outer irregular moons are almost certainly captured objects, pulled in from the Kuiper belt over billions of years. Some orbit prograde, others retrograde. Among them, Psamathe and Niso hold a record. They are the most distant known moons of any planet in the solar system. Their orbital period around Neptune stretches to 25 Earth years, a single lap around a single planet taking a quarter century. This is possible because Neptune's hill sphere, the zone where its gravity dominates over the Sun's, is enormous. Positioned so far from the Sun's gravitational influence weakens considerably, allowing Neptune to hold objects at extreme distances that no closer planet could retain. And that is Neptune, the planet mathematics found before eyes did, the world with winds that move faster than any other, driven not by proximity to the Sun, but heat generated from within, a planet whose interior may be producing diamonds under pressures 7 million times greater than Earth's atmosphere, a world whose magnetic field answers to different rules, whose storms come and go without warning, whose largest moon came from somewhere else entirely, whose outermost ring refuses to obey the physics governing every other ring system we've ever mapped. Neptune is the most distant and the most understated planet in our solar system. One flyby in 1989 gave us most of what we know about it. Everything since has come from telescopes and mathematics, the same tools that found it in the first place. There is almost certainly far more waiting out there in that cold, fast, diamond rain world at the edge of our cosmic home, and we've barely scratched the surface.